Students. So in this session we'll discuss about the IIR filter design. So the last sessions, the last 2 to 3 sessions, we discussed about the IIR filter design through analog filters. So the popular analog filters are IIR filter design. So the topic is IIR filter design through analog filters. So analog filters. So we have considered Butterworth, the popular Butterworth low pass filter, Butterworth filter. Okay, Butterworth filter. So based on the frequency response, it may be a low pass or high pass, band stop. Using the transformation technique is using the bilinear transformation technique, or impulse invariant technique. Okay, impulse invariant technique. So either BLT or IIM method. So the analog filters, Butterworth will take Butterworth filter. So the general steps to design a filter uh, from the given specifications. First, what are the given specifications? From the given specifications. So what are the specifications? Given specifications, the different parameters, the different parameters are different parameters such as ripples in the pass band, ripples in the stop band. Okay, either in term alpha P, alpha S, and the pass band H frequency, stop band H frequency, and you have to determine the cutoff frequency. So and find the magnitude frequency response for the Butterworth filter. So first you have to plot the frequency response and specify all the parameters. Then next one, if it is determine the order of the system. So normally order of the system. So if it is given any analog frequency, then you can do digital frequency. Analog filter to some cutoff frequency. Convert the analog filter to the digital filter cutoff frequency by using bilinear transformation technique or impulse invariant technique. So in which from the given specification you can find the order of the filter first. N, order of the filter. Okay, then using the transformation technique, first we have to do pre-warping. That is a conversion from analog to digital frequency. Conversion of analog filter to a digital filter. Digital frequency. So pre-warping has to be done. Then normalized, convert the normalized transfer function. Convert the normalized transfer function to denormalization. So frequency denorm. This is called third step is frequency denormalization. So pre-warping, find the order, then frequency denormalization. Next, convert your analog transfer function to digital transfer function. Either you can use bilinear transformation method or impulse invariant method. Then realization. Now H of Z in hardware realization. hardware realization, H of Z. So where the H of realization of H of Z, either you can use either you use that form 2, either you can use that form 2. It's a canonic structure. Canonic structure. There are different structures, that form 1, that form 2, cascade structure, parallel structure. So any one of the structures you have to realize. So these are the steps to design IIR filter. Okay. So we'll take one problem for IIR filter design. So the digital frequency is given specification. These are the given specification. In the specifications, digital cutoff frequency is given. Digital cutoff frequency omega is equal to 0.4 pi radians per second. So t is given 1 second. Okay. So for the given digital cutoff frequency in bilinear transformation, in bilinear transformation, we know that omega is equal to 2 by t tan omega by 2. Okay, actually this is omega t by 2. Okay, omega t by 2. So that is t is 1 second. Actually this is omega. If the sampling frequency is given, then you have to substitute uh, t value. So here 1 second. So omega t by 2 actually. Omega t by 2. Okay. So substitute 2 by t, omega is equal to 2 by t tan of, what is omega c is given, the digital frequency is given. So 0.4 pi by 2. So use calculator and compute the value for this omega, which is equal to 1.453. So simply don't write, you cross check each and every value out to, then you proceed to the next step. First use calculator, calculate this value and you check whether you are getting this value or not. Then the normalized transfer function for analog filter is given. So the H of S also is given specific in the specification. H of S, sorry, in the problem the H of S is given. Okay, H of S is given. Normalized transfer function is given by the normalized transfer function. The normalized transfer function H of S is given by 1 by S squared plus 1.414 S plus 1. So second order filter, this is second order filter. N is equal to 2. This is the order. A0 is always 1. The other coefficients A1 and A2. This is A0 is equal to 1. This is A1. A1 is equal to 1.414 A. So if N is equal to, from the table you can check. Then A2 is equal to 1. So in the previous lectures we have discussed about the polynomial coefficients. The polynomial coefficients for order from n equal to 1 to n. You can refer the table. Okay. So convert this filter. For this we have to do some. So what is a low pass filter? So normalization. Okay, will come. So now you have to do frequency denormalization. This is a pre-warping has done. Okay, this is the first step. Pre-warping. This is the first one. Pre-warping has completed. Pre-warping has completed. Second one, frequency denormalization. Frequency denormalization. So in that, for low pass filter design, Butterworth low pass filter. So low pass filter, for low pass filter, for from prototype to low pass filter, you have to put substitute S is equal to S by omega C. Okay, S equal to S by omega C. So now you can write H of S equal to 1 by S square, S by omega C the whole square plus 1.414 S equal to S by omega C, S by omega C plus 1. So now simplify this equation. 1 divided by omega C square. So simplify this one. Okay, simplify. So you will get omega C squared. Denominator term will be omega C squared. So S squared plus 1.414 S into omega C plus omega C squared. So this can be simplified. Omega C squared you do and cross check. So omega C squared divided by S squared plus 1.414 S into omega C plus omega C squared. This is H of S. What is omega C is computed? Omega C we computed 1.453. So 1.453 is omega C is 1.453. So you substitute the value of omega C. Okay. So substitute the value of omega C, which is equal to 1.453 the whole square into divided by S squared plus 1.414 into 1.453 omega C 453 into S plus 1.453 the whole square. So use calculator, compute the values properly. You will get the numerator term is 2.11 divided by S squared and multiply these two terms. Then 2.053 plus 2.1.5 square 2.1. So now H of S. Then the next step. So frequency rewarping, frequency denormalization we are done. Third one, cutoff. Substitute, this is a convert H of S into H of Z using the transformation technique, bilinear transformation. Either you can use impulse invariant or bilinear transformation. In the bilinear transformation, put S is equal to 2 by T Z minus 1 by Z plus 1. So again, so you can find H of Z is equal to, so the numerator is 2.11 divided by, so S squared. So 4 into, so the denominator will be Z plus 1 squared. We'll take S squared, so Z plus 1 the whole square. So 4 into Z minus 1 the whole square plus 4.05 to Z square minus 1 plus 2.11 into Z plus 1 the whole square. So substitute and compute the value of H of Z. So it is equal to 2.11 divided by 4 into A minus B the whole square, Z square plus 1 minus 2Z plus 4.05. So okay, Z squared minus 1 and plus 2.11 into Z squared plus 1 plus 2Z. Okay, so again simplify step by step we do. So 2.11 into Z plus 1 the whole denominator Z plus 1 the denominator term, so z plus 1 squared divided by multiply the term 4z squared, 4z squared plus 4 minus 8z plus is 4.05 plus 4.05 z squared minus 4.05, then plus 2.11 z squared plus 2.11 plus 4.22 z. Then simplify these terms. So 2.11 into z squared plus 1 plus 2z, the numerator term, a plus b the whole square, and z square you take a common term z squared. So here 4z squared, 4 plus 4.05 plus 2.1, so 4 plus 4.05 plus 2.11 and plus z, so minus 8 is z, and here plus 4.22 z and plus 4, then minus 4.05, then plus 2.11. So simplify step by step, so compute properly. So 2.11 limited term, so z squared plus 1 plus 2z divided by the z square into 10.21, 10.21, so this is 10.21 and plus z into minus 3.78 plus 2.01. So use calculator, compute properly, and so you can write. So this you take 2.11 z squared, take it outside, so 1 plus z minus 2 plus 2, sorry not 2, plus z minus 1 plus z minus 2 plus 2 z minus 1, so z1 2z divided by this z squared, so we can take it outside, z squared take it outside, 10.21 plus minus 3.78 z inverse, so 2 minus 1 1 plus 2 z minus 2, z plus 2 z minus 2 cancels, so 2.01 actually. So now these two terms will be cancelled. These two terms will be cancelled. So now it is equal to 2.11, multiply these two, 2.11 plus this 2 z inverse, 4.2 z inverse plus 2.11 z minus 2, the remainder term, divided by 10.21 minus 3.78 z minus plus 2 z minus 2. Okay, so again you can simplify 1 minus of, you know the transfer function how it will be, 2 point, the numerator 2.11 plus 4.22 z minus 1 plus 2 z point minus 2, okay, divided by 1. So this can be written as 1 in terms of 1 minus of 0.37 z inverse plus 0.196 z minus 2. So now, so the numerator also will be changed, sorry. So point 2 point, so not this one, 0 point, numerator will be 0.206 plus 0.413 z minus 1 plus 0.206 z minus 2 divided by, so this is h of z, okay, divided by 1 minus 0.37 z minus 1 plus 0.196 z minus 2. Transfer function h of z. So finally the coefficients, the feed forward and feed backward coefficients are determined. So only the feed forward and feed backward coefficients determines the uh, frequency response, so which approximates the frequency response closer to the ideal one. So now how this is a Z transform. The last step, how to realize your H of Z. Fourth step, realization. Realization of this IIR filter H of Z in using that from two structure. That from two structure. So already we taught that from two structure. So here n is equal to 2. So numerator polynomial coefficients m0 of the system, m is equal to 2 and n is equal to 2. So n only the number of poles are, you can say, order of the system. So order of the system. So you can determine how the poles locations also. So n is equal to even how the poles are located. Sometimes also maybe the how the poles are located. So using pi k is equal, n is equal to even. So n is equal to k plus 1 by 2 into pi by 2. You can use the pole determination also you can do. So whether the given system is stable or not. So the next ones, whether the first we'll do the stability. So before that, that from two structures. Okay, that from two structures. So how many delay elements are required to realize the system? Since n is equal to 2, n is equal to 2, second order, our number of poles is 2, which decides the number of memory locations in the realization. So two delay units are required. So the two delay units, Z inverse, another one, another unit delay element, Z inverse, two Z inverse. So the left hand side all pole system. Okay, so equal number of the poles and zeros here. So the denominator terms, the coefficients are, so this one you can write, okay, minus point, the coefficients are you got to write 1 minus of 0.37 Z inverse, uh, Z inverse minus 0.196 z minus 2. As per the standard transfer function, you can write. So while realization, so the two delay elements, the coefficient, the poles are A0 and A1 are minus 0.19 and other one is 0.3702. And the zeros of the systems are, the zeros of the systems are 0.206 and 0.413 that inverse and 0.206 z minus 2. Okay, so that from two structures can be realized Actually, the number of delay elements required is x of z. This is y of z. Okay. So this is the realization of hardware realization of your IIR filter with respect to the numerator denominator polynomial coefficients. The denominator polynomial coefficients are poles of the system and the numerator polynomial coefficients are the zeros of the system. Now in the final step you can determine whether the given system is stable or not. Stable or not. So for that we can determine the angle of the poles pi k. So for pi k, so for even and odd, you know that formula k pi by n for n is equal to odd, and pi of k angle of the poles can be determined for n is equal to even k plus 1 by 2 into pi by n for n is equal to even, where n is equal to n is equal to 0 1 up to 2n minus 1. So since n is equal to 2, you can determine 0 yes, 0 uh, uh, so which is equal to 0 comma 1 comma 2 into n is 2 minus 1. It is equal to 0 comma 1 4 minus 1 3, so 2 comma 3. Okay, now you can determine the angles. So pi since n is equal to even, use this formula pi k is equal to k plus 1 by 2 into pi by n. Okay, so k equal to 0. For k equal to 0, the pi 0 will be, so pi by 2, that is pi by 2 by n is 4 2, which is equal to pi by 4. Okay, pi by 4. So you can determine the poles. You can plot the poles. So you can write cos e per. This is can be written as angle. Also you can determine pi by 4. Then the location also you can determine e power j pi. There is a cos pi, cos j pi plus j sin pi, cos pi. So cos pi plus j sin pi. So use okay pi 0. So the pi value determined 45 cos 45 plus